Welcome students, welcome to General Science 101. Last lesson which we did with you, we looked at the Newton's third law and its applications. We said whenever you're applying Newton's third law, action and reaction are equal and opposite. We looked at Newton's pair of forces and we said whenever you have a Newton's pair of forces, there are certain things which happen with them. A, Newton's pair of forces are equal and opposite. They are opposite in direction. They are on different bodies and they're along the same line of action. We do not have one force in this direction with the force in direction because that is going to cause a non-Newton's pair of forces. Now, do remember one thing, whenever we are considering Newton pair of forces, we are always considering only two forces, the action and the reaction, and we are saying no external force is acting on them. We looked at mass and matter last time. We said what is mass? Mass is something which has matter in it. Matter, of course, is the something which has mass and occupies space. Matter exists in states like solids, liquids, gases, and of course we also included plasma in that. Then we looked at the statics of forces. We said forces which are at rest or forces which are causing motion. We looked at tensions in a string and application of the third law and the second law. We also started with application of momentum. We said there is another explanation to the third law to the second law of motion, where the second law of motion can also be stated as the rate of change of momentum is proportional to the force and takes place in the direction of force. Momentum and force are both vectors. They should have the same direction. So if there's a change in momentum in the positive direction, the force has to be in the positive direction. If the change in momentum is in the negative direction, the force has to be in the negative direction. And that is what we're looking at. We then started off with the law of conservation of momentum, that we said when two bodies collide in the absence of an external force, then of course the initial momentum and the final momentum has to be the same. Then in other words, normally we write that the product of mass and velocity of the first object plus the product of mass and velocity of the second object before the objects collide should be equal to the product of velocity of the first object and the product of velocity of the second object after the collision. Basically, in the physical sense, what it means was that when two objects had a collision with each other, the force, because it's action and reaction forces, because of the force of action, momentum of the second body changed. And because of the reaction, the momentum of the first body had to change by an equal amount. Today, what we are going to do is we are going to take this on further. We are going to apply it to different situations and see how it allows us to solve certain problems. Then we are also going to be looking at something which we have ignored so far, and that something is friction. We are going to be looking at friction. What are the advantages of friction? What are, of course, the disadvantages of friction? Normally, whenever you say friction, you have something which is going to be at a disadvantage because it is something which resists motion. And then we're going to be looking at methods of reducing friction. That is what we are going to do as we continue along. Now, like we said, let's start back again with the law of conservation of momentum. The law of conservation of momentum, as it states, is when two or more bodies collide, there is no net change in momentum, provided no external force acts on it. That is, if there is a change in momentum, that the net momentum before collision and net momentum after collision is the same. So momentum before collision, like we said, is m1u1 plus m2u2, and the momentum after collision is going to be m1v1 plus m2v2. Now, let us apply this case of momentum to a gun which is firing a bullet. Now, when we fire a bullet with a gun, the bullet goes in one direction, the gun recoils in the other direction. Now, what is the momentum of the gun and the bullet before firing? Of course, when you have a gun in my hand, the bullet is inside the gun, both are at rest. Therefore, the net momentum, of course, has to be zero because u1 is 0 and u2 is 0. Therefore, because both are rest, so m1 plus u1 plus m2 plus u2 has to be equal to 0. What is the momentum after I have fired it? This bullet moves in one direction, the gun moves backwards. So m1 v1 is the speed of the bullet, m2 u2 is the speed of the gun, because the law of conservation of momentum says the initial momentum has to be equal to final momentum. So 0 has to be equal to m1 v1 plus m2 v2, because m1 is the mass of the bullet, v1 is the velocity of the bullet, m2 is the mass of the gun, v2 is the velocity of the gun. And when we rearrange this equation, we get m1 v1 is equal to minus m2 v2. Very simply, the minus sign tells us that they are vectors which are in opposite directions. Therefore, if the bullet is moving in one direction, the gun has to, of course, move in the opposite direction. By rearranging, we can very simply find out the velocities. The velocity 1 is going to be m2 minus m1 over v2 with a minus direction, and v2 is going to be m1 over m2 into v1, again in the opposite direction. So basically, we can then find out how the gun will recoil. And that is one of the ideas when you have, why do you have very big guns or very heavy guns? Because the heavier the gun, the less the recoil will be, because if you're going to have a bullet and a gun of equal weight, they are going to move apart at the same velocities. You do not want the gun to move at a very, very fast velocity. Then, of course, the poor soldiers will have to run after the gun to bring it back. And by that time, of course, the situation might have passed away. You have a slide on your screens which shows you another example. There's a light truck with 2,500 kilogram mass. It is traveling at 72 kilometers per hour. Now, you have a light truck. It now strikes a car which is stationary at rest. The car which is stationary at rest, these two truck and the car, of course, have an accident and then move off together after the collision. We have to find out how it will move after the collision. We have our data information. Mass of the truck is 2,500 kg. The mass of the car is 1,000 kg. The initial speed was 72 meters per second, kilometers per hour, and the initial speed of the second car is that it is rest. And after collision, V1 is equal to V2. That is what we have to find out. And the car and the truck are now locked together. We have our relationship that the initial momentum and the sum of the final momentum has to be equal. And momentum, of course, is mass into velocity. And the relationships we are going to use, first we convert 72 kilometers an hour into meters per second. And that very simply is 72 multiplied by 1,000, because 72 kilometers divided by the number of seconds in 1 hour, which is 3,600, which is giving us 20 meters per second. So we have our truck moving at 20 meters per second. It hits the car, which is at 0. So the initial momentum would be 2,500 into 20, which is 3,500 Newton seconds, multiplied by the velocity v2. The initial momentum, of course, will be 2,500 into 20, which is 50,000. The final momentum is 2,500 multiplied by the mass of the two cars, which is 3,500. So 3,500 V2 is equal to 50,000, giving us a velocity of something like 14.2 meters per second, which of course is somewhat what we observe, that whenever an object comes and strikes another, speed has to go down. So we found that the speed went down from 20 meters per second to 14 meters per second square, which is corresponding to what we look. Now, let me pose some food for thought. What would happen? Why does it happen that when I'm blowing a balloon, I release it, the balloon moves forward? Why does it move forward when it is released and the air comes out in one direction, the balloon moves in the other direction? Now, if you remember, we said air is also matter. Now, we already have stated that matter has mass. Matter is something which occupies space, it has mass. Therefore, when air is coming out, mass is coming out, it has certain velocity. Therefore, we have momentum in this direction, and the reaction of that momentum is pushing the balloon forward. We apply a similar situation to rockets in space. In space, normally, if I am walking on the ground, I push the ground backwards, the ground pushes me forward, and I walk forward. However, when there is a rocket in space, there is nothing to push against. So how does a rocket move? How does a rocket increase its speed or decrease its speed? Movement is easy, because if we had initial velocity when we launch the rocket, it will continue moving as Newton's first law states. But how does it increase or decrease its speed? How does it change its direction? Very simply, it ejects hot air from the nozzles of the rocket. That means it is ejecting mass with a certain velocity. So m1v1 goes in this direction, and the rocket is moving in the opposite direction. That basically wraps up our discussion on momentum. Now let us start looking at something else. What we're going to be doing is, if you have a car moving on the road and the driver eases off the accelerator, he's not pressing the brakes, still we find that the speed of the car becomes less and less and less. What is it that is making the car lose speed? And another question which normally we pose is, why is it easier to drive on a dry road than on a wet road? The answer to this question lies in an inherent property of matter, which is friction. Now, whenever, for example, this is a box, I want to move it in this direction, then there is something which is preventing this from moving in this direction. That has to be in the opposite direction, and we call it as friction. Friction is basically a force that acts in a direction opposite to that of movement. And friction normally is whenever you have two surfaces which are moving across each other, one first surface and another surface, whenever two surfaces meet and they are moving across each other, you have something which is called friction, which is technically opposing the amount of force which we apply to it. It is something which opposes, which does not allow motion to take place. What exactly happens is that whenever two surfaces meet, there are contacts at different points, and you have electrostatic forces, positive charges in one, negative charges the other, which are attracting each other, and therefore having some cohesion, therefore we require some force in order to break them. They are microscopic contact points. Now, if I look at this object, there are going to be four forces acting on this. Now, if I'm applying a force, then I have the driving force in one direction, friction force in the other direction, weight downwards, and a reaction upwards. But because this calculator is not moving upwards or downwards, we say the reaction and the weight, of course, are equal. Therefore, we do not consider these as such. Now, friction has certain advantages. The world we live in, if friction was not there, would have been a very, very different place, because frictions allow vehicles to move. How do they allow them to move? Tires of the vehicle push the road backwards, the vehicle moves forward. Vehicles can apply brakes. It allows vehicles to stop, because friction is something which is opposing motion. When you apply a brake, the friction between the road and the tire increases, and which causes a force in the opposite direction, decreasing the speed of the car, and it can stop. Machines, they can work because there is friction. Because when I turn a machine, there are two items sticking together. Because there is friction, it will allow it to move. It allows this thread in this quartz to remain as it is. Otherwise, if there is no friction and I would dust it, all the pieces of thread would just fall off. We can do work very simply because there is friction. Because otherwise, I just simply could not walk. There is no way I could push the ground backwards and hence move forwards. I can, for example, hold a pencil in my hand. I can only hold it in my hand because of friction between my thumb and the pencil. A pencil can be held. I can knock a nail in the wall, and because of the friction, the nail will remain there. If there was no friction, it will just move into the wall and it will not serve any purpose whatsoever. However, friction has lots of disadvantages. The basic disadvantage there is that whenever there is friction, I have to apply a force to overcome that friction. Now, if a force moves a certain object a certain distance, then work is done. And if there is friction, the net amount of work which I'm doing is greater than that would be if there was no friction. Therefore, energy is lost. Machines wear and tear because of friction. Instruments become outdated or they become damaged due to friction, because if I have a machine which is working, like a car engine which is turning, whenever there is friction, in order to overcome that friction, force has been applied and the wear and tear of machine takes place. And because energy is being wasted, you require more fuel. Fuel is used to overcome friction, and therefore the cost of running that machine or running that equipment in the presence of friction increases. And because that cost increases, wear and tear is there, sometimes parts have to be replaced and replaced at a larger frequency. Of course, we also require lubrication. Lubrication is a technique with which we reduce friction, and that is why we have to lubricate things. So in other words, that overcomes friction. Now, if we're looking at a free body diagram of friction, let us say that I have an object which is on the table and I want to apply a force to it. Now, if we look at the free body diagram, there are 4 forces on it. The weight is acting downwards, the direction of the table is upwards. I have a driving force which is trying to push it in this direction. The friction force is in the opposite direction. If we look at the free body diagram where the magnitudes of the forces are going to represent friction, then the arrows of the forces will tell us which force is larger and which force is smaller. Of course, when this object is on the table, the force downwards and force upwards are equal because the object is not moving in that direction. However, for friction, sometimes we say that if I apply a force and this object does not move, in other words, I push a wall, I can apply a very large amount of force. However, the wall refuses to budge because the frictional force is greater than the force I'm applying. Remember, in this case, we are not looking at Newton's pair of forces, because the action and reaction, the amount of force I apply, the amount of force which the wall is going to apply on me are going to, of course, be equal and opposite. But there is when we are looking at friction, unless I overcome friction, that object is not going to move. I can apply a certain amount of force without disturbing this calculator, very simply because the force I'm applying is insufficient to overcome the force of friction. If it overcomes the force of friction, the object then starts moving. Now let us see, this is a calculator. It is on the table. There are forces which are going, it has weight, therefore one force is downwards, it is acting on the table. There's one force, the reaction is upward, and because these forces are equal, this object will remain here. However, when I apply a force under which the calculator will move, the force is going to be, if force is sufficient to overcome the frictional force, then the calculator moves. If the force is insufficient to overcome the frictional force, the object does not move. A similar example is when I'm pushing against a wall. Now, frictions, of course, are of different types in different situations. You have static friction. Static friction basically is friction of objects which are at rest. In other words, the force of friction there is larger than the force which is causing movement. You have kinetic friction. This is the friction when two objects are moving or two surfaces are rubbing against each other, so movement is there. So whenever an object is moving, then there is a friction force between the two moving objects, depending upon what surfaces they are. Now, one thing you should remember is that kinetic friction is always less than static friction. That is why whenever we are trying to shift something, it takes a slightly larger force as to cause motion than to maintain motion. Then, of course, we have rolling friction. In rolling friction, basically, an object is rolling along the ground because when an object is rolling around the ground, the contact surface between the object, which is a ball, and the ground is very, very small. Therefore, rolling friction is normally very minimal. Now, because in a rolling friction, the friction is very minimal, therefore it has got wide applications in ball bearings. In ball bearings, you have got a round object with very small round objects in it, and therefore, because the minimal amount of contact surface is there, friction is very minimal, and we can then save energy. Of course, we have One other type of friction, theoretically it is not friction, known as limiting friction. Whenever the word limiting friction is used, it means that we have now applied a force which just overcomes friction. A slight more increase in force is going to cause motion. Limiting friction is very, very essential in solving problems, because when we are solving problems, we always apply a limiting case to find out what is the maximum amount of force or load we can apply on an object. Another type of friction we have is sliding friction. Sliding friction is, like the word says, is only applied when an object is sliding on another object. Now, when we look at how to calculate friction. Now, friction basically depends upon the weight. The larger the weight an object is applying on the surface, the more the friction would be. Just like I have a book or a calculator, the book has a larger mass, so it is pressing with a larger force, and because it is pressing with a larger force, the friction amount between the surface on which the book is resting and the book itself is going to be very, very large. Therefore, we have a direct relationship that the friction is directly proportional to the weight. Now, in order to understand, because the weight and the reaction of the surface are identical, we normally say friction is directly proportional to the reaction of the surface. Because we want to relate it to the surface, so F is proportional to R. We say F is equal to mu R, where mu is the coefficient of friction. Depending upon which friction we are looking at, we say F, the force of friction, is going to be equal to mu Kr, where K is the kinetic friction, or it is equal to mu Sr, where mu S is the static friction. Like we have said, the mu static friction is slightly larger than the kinetic friction, and it will depend upon what relationship. Now, what do we do in order to reduce friction? Because like we've already stated, friction has got relationships in which we want to reduce friction, because friction is consuming energy. In certain areas, certain applications, we would like to increase friction. For example, in brakes, when we want to brake a car, we want to increase friction so that we can brake in a shorter period of time. However, in certain areas, in machines, in engines, we would like to decrease friction because we do not like to waste energy. What we can do is we can polish the surface. The smoother the surface, lesser the friction, because the amount of contact points would become lesser. We can apply a lubricant. Now, what does a lubricant do? Do remember that the coefficient of friction depends upon what surfaces are rubbing. Normally, the coefficient of friction between a solid and a liquid is very low. That is why when you lubricate it, you oil something, you are reducing the amount of friction available, and hence the movement becomes smoother, energy wastage becomes less. We can use rolling objects or ball bearings in case you have to have very high speed. So examples are in your tires, you have ball bearings because you do not want friction to take away a lot of energy and thus the tires. We can also, of course, streamline the object. If you look at aeroplanes and ships, you find they have a particular shape. They are pointed at the beginning where the majority of the friction is, where it is trying to penetrate the water, penetrate the air. So streamlining an object is another way to reduce friction. You might have seen along the roads that high-performance cars more or less have the same normal shape in front of the car, that they have a shape which is streamlined. In other words, this is designed so that friction is reduced. Let us look at a practical example of friction. Let's look at a numerical that you have a motorcyclist which is moving at a uniform road with a certain velocity. The engine is providing a certain amount of force. In our case, 350 newtons, and the amount of friction is 0.6. Because it is a constant, it would just have no units to attach to it, and the rolling friction is 0.75. So let us see what is going to be the amount of friction which is going to be on the motorcycle. So the F is equal to mu R, mu static friction, mu S multiplied by mg, which gives us 0.75 into 350. So the static friction in order to start the motorcycle from rest would be 262.5 newtons. So that is the amount of force the engine would have to provide just to start the motorcycle. But once the motorcycle is on the road, then of course the force of friction would be mu kinetic multiplied by rg mg. In this case, the kinetic friction, of course, is going to be 0.6. So when 0.6 is multiplied by 350, you get a value which is 29.4 newtons, which is the force which is being applied by the car. So what we have done in this lesson, in fact, this and slightly the previous lesson, we've looked at the Newton's third law, we've looked at Newton's pair of forces, we've looked at the difference between mass and matter, we have looked at tension in a string, momentum, law of conservation of momentum, friction, and means of reducing friction. That basically wraps up this lesson, and we are going to now continue on into the further next lesson, which is lesson 9 as part of this lecture. And in this, what we are going to do is we are going to be looking at energy and forms of energy. Now, in the previous lesson which we had with you, we looked at force, inertia, we looked at the Newton's laws of motion and their application, we looked at momentum, and we looked at friction. We said force is something which is going to cause or does cause a change in motion, it compresses or decompresses. Inertia is something which is the inherent property of mass, that it resists the change in motion. Therefore, in the absence of force, it is going to remain in its state. We then went from mass, and trying to define mass, we said mass is something which contains matter. And matter is, of course, like we know and we have discussed in the last lesson, is something which occupies space and has mass. Matter can exist in a variety of states. You can have a matter in the shape of solids, liquids, gases, or of course plasma. In the previous lesson, we also looked at the 3 Newton's laws of motion and their application, and basically we formed the basis of how a force is applied and how this application of force causes an acceleration or increase or decrease of speed. And as a further to the Newton's 3 laws, we looked at momentum, and we said, okay, momentum is something which is used whenever you have a collision of bodies. Momentum is defined as mass into velocity, and because it is defined into mass and velocity, it is the capacity of an object to exercise force on something. And because action and reaction were equal and opposite, we combined all of these into the statement of the law of conservation of momentum, which stated that the initial momentum before a collision and the final momentum after a collision have to be equal, and allowing us to apply to different situations. We then looked at friction. Frictional forces, we said that frictional forces can be of different types. There is rolling friction, sliding friction, you have friction static, and friction which is kinetic. Static friction, of course, being exercised when objects are at rest. Kinetic friction when objects are sliding across each other, or there is movement between two surfaces. Sliding friction is when an object slides. Rolling friction is when an object is rolling, or it is for circular objects. We looked at different ways in which we could reduce friction. We looked at advantages of friction, and we looked at disadvantages of friction. We said friction in certain cases is advantageous. It is advantageous that you have a car, you want to make it stop, you would like to increase friction. In other words, you have to apply the brakes. In machinery and in other pieces, because equipment, whenever you have friction, you are going to be losing energy, and of course we do not want to lose energy. Therefore, we have to reduce friction. Friction can be reduced by either polishing the surfaces so as to remove any kinks, and therefore the movement should be smoother. We can remove friction by lubricating it, because we know whenever there is a liquid present between two surfaces, the amount friction, coefficient of friction goes down. Hence, the force required goes down. Of course, we can also use the rolling friction, because rolling friction is minimal in the different types of frictions. That is why we use ball bearings in different applications. What we are going to be doing today is we are going to be looking at the concept of work, power, and energy. And we are going to be continuing to discuss these as we go on. Now, what exactly is work? When do we say an object or a quantity or an entity does work? this is an object which is lying on the table. Is it doing any work? It is, of course, not doing any work because it's just lying on the table, resting, not doing anything. Now, in physics, we define work as the work which is useful. Because we are looking at useful work, we would look whether that work is exercised in a direction we want it to do. For physics, we define work as the product of force and displacement. If I apply a force to this object and this displaces from point A to point B, we say work has been done. So work is defined as force into displacement. Now, for work to be done, two things have to be kept in mind. A, that the force which is acting on the body has to be a net unbalanced force. Because if the force is balanced, in other words, I have action and reaction forces which are equal and opposite, that means the net force on the object is zero. Because the net force is zero, of course, work will not be done. And the object has to move a certain distance in the direction the force is applied. Work, therefore, is defined as F into S, or force multiplied by distance. Work is a scalar quantity, and its units are Newton meter or joules. Now, what about forces? What about the action-reaction forces? Now, as we have seen on the slide, I have a representation of the slide, there are three forces acting on an object. One force which is acting downwards, which is towards the center of the earth, which is the weight of the object, which is equal to mg. We have a reaction which is vertically upwards, which is r is equal to mg. These are two forces which are, of course, balanced on a Newton pair because the surface on which this is resting is not moving. It is not allowing this object to move in the vertical direction. The object is moved from point A to point B, and the displacement x is in the direction of the force. Therefore, this is the force F which is causing work. As far as physics is concerned, we are doing work only in one direction. Now we have a couple of cases to look at. A, the conditions for work to be done: there should be a force on the body, and the body should cover a distance s in the direction of force. So we say work is equal to force into distance, where the force has to be not equal to zero and the displacement has to be not equal to zero. So the force has to be greater than zero and the displacement also has to be greater than zero. Case 1, let us say F is equal to 0. Now, if F is equal to 0, there is no force applied on the body, then work as it is F into S has to be equal to 0. Of course, when we look at the object, I have no application of force on it. It is not moving. It is just resting in one place, and therefore I say the work is being done. In the second case, I apply a force. The table does not move. Have I done any work? I might say I have applied a force, I have become tired. But as far as physics is concerned, because the object has not moved in the direction I have applied a force, I am applying a force downwards, the table refuses to move downwards, therefore the amount of work I have done, of course, is 0. That is, the work has not performed anything significant. Now, when we are looking at gravitational force, let us say this was an object which is at this position. There is a weight which is acting downwards. It moves under the action of force a certain distance. So, what is the force which is being applied on this object? The force, of course, is gravity, and we know it's the force of the weight. Now, W is equal to mg. The displacement, of course, is x. Object has gone from point A to point B. It has covered a certain distance. Therefore, some work has been done. And in this case, when an object is moving under gravity, we say F is equal to mg. The displacement has to be equal to x. And the work done, W, should be equal to mgx. Here we have to distinguish between the two things. However, in physics, you will find quite a lot of such confusions, which are not confusions, but you have to get used to them. We use W for a weight, we use W for work. only the relationship when you're looking at it. W when used for weight will be equal to mg. W when used for work, W when used for weight is mg, and W when used for work should be mgx or mgh as we look at the work for that particular point. Let us look at the relationship we had looked at about 3 lessons back. We are going to be using that. This is the trigonometric or the coordinate geometry relationships, that whenever you have a right angle triangle, then the relationships between the triangle and the angle theta, sine theta is y over r, cos theta is x over r, and tangent theta, of course, is y over x, and the Pythagoras theorem, x squared plus y squared is equal to r squared. Why do we need this? Because sometimes the force is applied at an angle. What do we do? For example, we have an object. I'm not applying a force directly parallel to the surface, but at an angle. Because I'm applying the force at an angle, we have this normal situation like, for example, this is a lawnmower and I'm pushing it at an angle, but the object is moving straight. Then in this case, we have to use the relationship cosine of theta. Like on the slide which you are seeing is that we have a force which is being applied at an angle. So the weight is downwards, the reaction is upwards, the force is at an angle, but the force in the direction of the motion is F is equal to F cos theta. So F cos theta is the force which I'm going to use for finding out the amount of useful work which I have done, because I might have applied a force which is larger than F cos theta, but for our purposes, we are going to look at only the useful work which is done, or the force in the direction of the displacement. Now, we have said the factors on which the work depends would be A, it will depend upon the force which is acting on it. It will depend upon the distance covered in the direction of the force. And third, it will depend upon the angle on which the force acts. So W is equal to F dot S. And because we have said in our case, W is going to be F cos theta multiplied by S. Because F cos theta S are all scalar quantities, we can rearrange them and we find the general relationship of work, that work is equal to force into distance multiplied by cosine of theta. Now, how does cosine of theta affect the work? Now, let us take different cases. Let us take a case in which theta is 0. In other words, the force is in the direction of the displacement. Now, putting the values of theta is equal to 0 in the equation, what we get is when theta is equal to 0, W is equal to Fs cos theta. Now, cos theta is 0, and when you look at the tables of the cosines, we find cosine of 0 degrees is 1. So the work has to be equal to Fs. In other words, we get the maximum work whenever the angle between the displacement and the force is 0. In other words, both are in the same direction. Let's look at a second case where the force and the displacement are perpendicular to each other. If the force and the displacement are perpendicular to each other, then we have theta is equal to 90 degrees, W is equal to Fs multiplied by cos of theta. In this case, it is 90 degrees. If we look up in the cosine tables, we find cos of 90 is 0, and in other words, work is 0. Now, if I want to push the calculator in this direction, but I'm applying a force vertically downwards, then the calculator is not going to move, or in other words, I'm not going to do any useful work. This is from the point of view of physics, because what we are interested in is in which direction to apply a force to get what type of work out of that system. Let us take a third example. In this example, the angle theta is 180 degrees. In other words, this is the direction in which I want to move, but the force being applied is in the opposite direction. Do we have such of an example in real life? Yes, we do have an example in real life. We have two students who are in a tug of war. This student wants to pull the rope in this direction. This student wants to pull the rope in this direction. However, this student being stronger, this moves in this direction. Now, when we look into the other student, then the force is in the opposite direction to which that student wants to move. I want to pull the rope towards me, but because the force in that direction is larger, I'm being dragged towards that force. So in this case, we have 180 degrees. When we put the values in our formula, we find W is equal to Fs cosine of 180. Looking up into the cosine tables, we find it is Fs multiplied by -1, or W is equal to minus Fs. In other words, we have negative work. In other words, whenever we have negative work, it means we are not getting worked in the desired direction. For all other angles, as in the cosine table, the value goes from -1 to 1, we will have values of the work which is less than 1. In other words, whenever you have force and displacement not in the same direction, the net amount of useful work you will get, or intended work as we say, is going to be less than the actual one, Ws. And that is as it is true. What is the unit of work? Work is the scalar quantity, and its unit are in joules. Now, what exactly is a joule? If you look at W is equal to F dot S, the unit of force is a Newton, the unit of displacement is a meter, so the Newton meter is 1 joule. 1 joule is defined that the work of 1 joule will be done when 1 Newton force acts on a body and it moves a distance of 1 meter in the direction of force. So you have 1 joule of unit, 1 joule of work is done when 1 Newton force acts on an object and makes it move a distance of 1 meter in the direction the force is applied. 1 joule is a very small unit. We have larger units which we use in everyday life. We have a kilojoule, which is of course a 1000 joule, or like we say, it is 10 to the 3 joules. We have a megajoule, which is of course a million joules, or 10 to the 6 joules. These are larger units which are used in physics, and as we go into thermometry, we will find that we will be using these units more and more often. Now, let us look at 2 numerical examples which will tell us how we can do this, apply this relationship, work is equal to force into distance. Let us say a laborer wants to push a crate which has got a certain weight, and he wants to push it a certain distance. In the numerical, the crate is pushed through a distance of 20 meters. The force which the laborer is applying is 250 newtons. We just have to see how much work is being done. The force applied is 250 newtons. The distance moved is 20 newtons, and the work is what we require. This is the data we have. The formula which we use, of course, is a standard formula, that W is equal to F into S. So the work done is going to be 250 into 20, which is 5,000 joules. So in the laborer applying a force of 250 newtons moves the object 20 meters in the direction of the force. He does a useful work which is 5,000 joules. Now the same laborer now wants to take this object at an angle. He now is continuously applying the force in the same direction, but the crate is now moving upwards at an angle, like it is shown on the slide. In this case, we will use the general equation, which is W is equal to Fs cos theta. We have our data. The force applied again is 250 newtons. The distance covered is again 20 meters. However, the angle of the ramp is given as 60 degrees. So applying it in the relationship, W is equal to Fs cos theta. We find W is equal to 250 multiplied by 10. We look up into the cosine tables, and we find that the cosine of 60 is 0.5. So the amount of work done is going to be 2,500 joules, which is of course less than the earlier work, even though the laborer might become more tired. But we will go into that later on, because what we are looking at is the amount of useful work in the direction of the force. Now, normally in normal everyday usage, we do not use work as joules. However, which we are using is power. That is another thing which physicists are interested in, and that is power is defined as the rate of doing work. In other words, power is defined as work done divided by time taken. Now, work, of course, was a scalar quantity. Time is a scalar quantity. Therefore, power also is a scalar quantity, and its unit is the watt. Now, what is exactly watt? Watt is that if 1 joule of work is done in 1 second, then the power of that component or that instrument is 1 watt. We have larger units in everyday life. We use kilowatts, which are 1000 watts or 10 to the 3 watts. We also have megawatts, which is 1 million watts or 10 to the 6 watts. Now, let us look at an example, a numerical, that a motor pumps 2000 kilograms of water in 1 hour to an overhead tank, which is about 50 meters height. It's at the height of a 5-story building, and 50 meters, it just pumps from water to a height. We have to find the power of the motor. Now, the formula which we are using, remember we said work against gravity is going to be mgx. So power is defined as W divided by T. The data which we have is the mass is 2000 kilograms. The force applied, of course, is going to be mg, which is 2000 multiplied by 9.8, giving you 19,600 newtons. The distance moved is 50 meters in the vertical direction, and the time taken, of course, is 1 hour, which is 3600 seconds. And of course, the work done is going to be mgx, which is 2000 multiplied by 9.8 multiplied by 20 is 392,000 joules, and the power which is being provided by the motor is 392,000 divided by 3600 is going to be 108 watts. So something like 110 watts of power is basically required because it is a very long period of time. Another way of measuring power, which normally is very popular among students, is that the students measure their mass and they run up a flight of stairs, which let's say is about 20 kilometers, and they time a stopwatch to find out how much power is being developed by the student. Let us, in our example, we have a 65 kilogram student running up a height of 20 meters in 35 seconds. We have to find the power developed. The data which we have is mass is 65 kg. The force applied, of course, is mg, which is 65 into 9.8, 637 newtons. The distance moved is 20 meters. The time taken is 35 seconds. The work done in going for the 65 kg student up a height of 20 meters would be 65 into 9.8 into 20, giving you something like 12,740 joules. That is the amount of work done. The time taken is 35 seconds. So the power developed by the student, P is W by T, is 12,740 divided by 35, should be around 364 watts. And basically, then looking at the different students, you can find out what this is. Now, the crux of this matter is that we have now to go into what exactly is energy. Energy is the ability to do work. We require energy to do any type of work. And the unit of work and the unit of energy, of course, are the same. Because ability to do work is energy, therefore they have the same units. And energy also is the unit of work, unit of force multiplied by unit of displacement, which of course is a joule. So the unit of energy and the unit of work is the same. Now, what exactly is energy and what types of energies we have is something which we are going to go into the next lesson. In this lesson, what we have done is we have looked at work, we've looked at power, we've looked at work, and work we have stated is that work is only done when a force is applied to an object and it moves. So conditions for doing work are A, a force has to be applied, B, the object has to physically move its position. You cannot apply a work, or you cannot do work if you are applying a force to an object which does not move. We will continue this discussion later. Thank you very much. Khuda Hafiz.